All right, so I'm going to get started. Thank you everyone for showing up this afternoon on this half of the presentations going on. Looks like machine learning is enough of a buzzword that even for, as Rich Hickey put it this morning, cranky old programmers, it's enough to draw you in, which is really great. For me, I came from a Python background in machine learning, actually. So I worked in Python and machine learning for 2 years before moving over to Clojure to do machine learning. And just based on my own experiences, there's a pretty large area of intersection between functional programming and machine learning that's been left largely unexplored. And this intersection is particularly interesting between machine learning and Clojure, which is why I want to give this talk on building machine learning models with Clojure and Cortex, which is a machine learning library built for Clojure. So this talk is largely going to be split into 3 parts. We're going to start off by talking about what machine learning is, other than the buzzword that got you all into this room. We're going to talk about why we want to use Clojure specifically, and why I said that the intersection between machine learning and Clojure is especially promising moving forward. And finally, we're going to talk about how to use Cortex, which is the library that we can use to do machine learning in Clojure. And at the very end, as long as we have time, I want to walk through how to build this baby classification model in Cortex that can hopefully show off how you can perform machine learning in practice, and also why some Clojure techniques fit in so neatly with machine learning in practice. So to get started, I want to talk about machine learning. Some people in this room may already know a lot about machine learning and know exactly what it is. For the rest of you, you've probably heard a lot about machine learning and what it does, but not too many details about how it works in practice. So you probably know that it's what powers self-driving cars. You know it powers Google Search. You know it powers Amazon recommendation engines. You know it powers Apple Siri. You know it powers all of VC funding in Silicon Valley. And if any of you are interested in any of those, particularly the latter, you've probably gone on Google and searched around for what machine learning is, which means you've probably landed on this page, which is perfectly legitimate. It's my go-to site as well. So everything that I'm going to talk about with machine learning and neural nets, I'm going to draw from this page. So the first thing we want to do is establish a little bit of context around what machine learning is. And according to Wikipedia, it's an application of artificial intelligence. So that gets us to our first point. The current definition of artificial intelligence is pretty broad. There's a large scope of what can and cannot count as artificial intelligence. But probably the most useful definition for us is the challenge of trying to get computers to mimic human behavior and carry out tasks that are traditionally associated with human-level intelligence or cognition. And this can mean a wide variety of things. But before the advance of machine learning techniques, and before machine learning started taking over the world, most of artificial intelligence took place in the form of expert systems. So this happened throughout the 80s, the 90s, even a lot of the 2000s. And how expert systems achieved artificial intelligence was by essentially teaching computers how to think like humans. We would explicitly program in details of how the computer was supposed to reach its conclusions by teaching it as if we had expert knowledge in the field, and we were giving the expert system the same knowledge. So if I was working at a quantitative trading firm, I might have a rule that says, okay, if Apple shares ever drop down to $150, let's sell 1,000 shares. So if we combine a bunch of these rules that human experts have come up with, domain experts have come up with, and hard code it into the system, we can achieve the system that can mimic human behavior pretty well. And we can achieve a system that can mimic intelligence pretty well. And this has been the dominant paradigm ever up until the 2010s, I'd say. There are only a couple problems with the idea of expert systems or rule-based systems. The first one is that in a lot of cases, humans don't actually really know how to think. Like, stock markets are a perfect example of this. Like, we want to achieve intelligence here, but humans don't actually know exactly how to reach it, so we can't hard code the instructions in. The second problem is that sometimes humans know the result, but we can't explain how we've achieved the results. And this becomes particularly apparent in the fields of natural language processing and computer vision, where we can very easily recognize a cat, but we can't explain to each other why we can recognize a cat. So if that's the situation that's going on, it's very difficult for us to hard code this into an expert system. We can't have a set of rules that teach the computer exactly how and when to recognize something as a cat or a dog or a human face in a conference room. So when we can't teach the computer how, we have to let the computer come to the conclusion itself. So in machine learning, instead of programming in the instructions for how a computer reaches a result, we just feed the computer the results we want it to see. So we say that we feed the computer images of cats and tell it that it's a cat. Or we tell the computer that on some day, Apple shares dropped to $150 and we sold 1,000 of them, and this is what happens. And we let the computer itself come up with the reasoning process, come up with the how you reach the conclusion. So that's a contrast between expert systems and machine learning. Machine learning takes in data, and from that data, it learns an association from them. Within the sphere of machine learning, we have things that fall under deep learning and things that fall under not deep learning. Not deep learning are things you probably haven't heard of as much. You have support vector machines. XGBoost has become fairly popular recently. That's a gradient boosting machine. You have things like random forests, logistic regression, naive Bayes, a bunch of statistical models that work really well in practice. And in many cases aren't actually irrelevant now with the advance of deep learning. There are many use cases for all of these for which deep learning is an overkill for and perhaps not the best choice for. But these accomplish essentially the same things through the same techniques. For all of these models in machine learning, you're feeding in data, and at least in supervised machine learning, you're getting a prediction or a result out of them. Deep learning is the specific subsphere of machine learning that has been achieving a lot of the most advanced results that we've seen so far in artificial intelligence, and that's what we're going to be focusing on today. And deep learning just consists of these things called neural nets, which are very, very, very loosely based on human brains. That's how they were initially inspired. Nowadays, they've diverged pretty far from the analogy of a human brain, but that's still one way we can understand what neural nets do. But before we get into that, now that we've established the context for machine learning, I want to talk a little bit about what it looks like in practice. So Wikipedia tells us that machine learning involves a bunch of algorithms that can learn from and make predictions on data, which means that in practice, when you fit this into your software space or your technology stack, this happens in two distinct steps, the learning step and the predicting step. In practice, the learning step looks something like this. You have an algorithm that you've written up or that some library has written up, and you feed in a set of data and labels. So let's say we're trying to predict housing prices in Baltimore. We can have the label be the price of the house, the final price of where it's sold, and the data can consist of a bunch of information about the house, the square footage, the location, how many bedrooms, how many bathrooms, et cetera, et cetera. And you know all of this information could potentially be useful, but you may not know exactly how it relates together to get you your final house price. But you can feed these in separately to the algorithm, which can then generate a model through what right now to us is some black box magic. But you get a model out the other end that has learned to associate the data with the labels. So in your next prediction step, you can use this model that the algorithm has generated to feed in new unseen data. So say a new house rolls out onto the market, we can feed it into the model, and the model can make a fairly accurate prediction on what the final housing price is. And that's because through this algorithm, we've learned an association or a mapping between the data and the label, the data and what we're trying to predict. And when it comes back to machine learning and neural nets in particular, it's most helpful for us to think about this mapping as a function. So think about the housing price as a function of the data that we've been passed in. If we think about it in this light, then the entire goal of machine learning is to learn the function f that maps whatever input data you have to the prediction that you want to generate. Now, the reason neural nets are so powerful is because there's this thing called the universal function approximation theorem, which essentially says that a neural net with a single hidden layer, and we'll get into what that means in just a little bit, theoretically has the power to approximate any arbitrary function there is in the real space, which means it can approximate something super simple, just a one-to-one mapping between x and y, a linear, just a single line. It can approximate more complicated relationships between these two variables, and it can approximate functions of any dimensional space you want. So this is 3 dimensions. I can't display a 4-dimensional image up there because it doesn't exist as an image, but it can do 4 dimensions, 5 dimensions, and in machine learning, and with deep learning in particular, it tends to get up to hundreds of dimensions or thousands of dimensions. And the idea is that, in theory, these neural nets can approximate any function mapping between however many dimensions of input data you have and the output that you're trying to predict. Given enough examples and given enough of a training data set to learn from, your neural net can make accurate predictions for anything in the future. And the way it does this, and I don't want to get too deep into the weeds here, but the way neural nets make these predictions is through a series of multiplications, additions, and nonlinear transformations. So this is a perceptron. It's a single unit of a neural net. And the output is generated after passing a set of inputs. So we have 3 inputs here, x1, x2, and x3. You multiply each one by some weight value, you add them all together, and you pass it through a nonlinear, what we call activation function, in this case sigmoid, which just squashes the number onto a scale of 0 to 1, essentially. And that's how you get your output y. In machine learning and in neural nets, the whole goal of learning is to learn the proper weight parameters here. So W1, W2, and W3. In other words, what values do we multiply with the square footage of a house, or the number of bathrooms, or the location? What values multiplied by all of these and added together and passed through another activation function can get me the correct prediction at the very end? In this case, it looks fairly simple because there's only 3 values to predict. In neural nets, as you size up, because this is just 1 unit, you can get a whole combination of all of these. This is still a very small neural net. It has 3 inputs in a single hidden layer. And you can see that with each node in the neural net, it's the same perceptron as we've seen earlier. It has a bunch of inputs coming in and 1 output going out. It just happens to be fully connected among every node to every other layer. And we do the same exact process of transformation in all of these, except we learn maybe a different set of weights that are associated with each of these nodes. So once we have this is our basic outline of what a neural net is. It's supposed to model the neurons in our brains and the way our thoughts flow through our brains. To my very, very limited understanding of neuroscience, this isn't accurate whatsoever, but it's a very useful analogy for how computers, quote unquote, think. So this is machine learning. Deep learning is a fat neural net, basically. Once you have more than 1 hidden layer in a neural net, it becomes a deep neural net, and then you have, quote unquote, deep learning. So you can add an arbitrary number of hidden layers in between, and you can also get different types of layers in between. So these are all fully connected linear layers. You can have things like convolutional layers, which are useful for image processing. You can have recurrent neural nets, which are useful for natural language processing. But they all have the same general structure. You have a series of nodes and input values that flow through these nodes, and a series of weights that are associated with each node that you learn in order to make your prediction. So that's what machine learning is. You have a bunch of data, and you want to teach the computer how to reach a conclusion from that data. And the computer is responsible for learning that itself through this process. So I now want to talk a little bit about why we are introducing Clojure into the conversation of machine learning. At ClojureConf, it's a pretty simple reason. You guys are all Clojurists. This is like the only way I can convince you to do machine learning. Outside of Clojure, this is definitely not the case. I'm sure none of us are fans of reinventing the wheel, and it happens that machine learning's wheel has been invented many, many times over outside of Clojure. We already have a suite of, honestly, very good libraries that do machine learning in a variety of other languages. So TensorFlow is written by and powered by and used by Google. I believe Torch is used by Facebook. And a bunch of these other libraries are being used and supported by a wide variety of other researchers and industries out there. The vast majority of these are written and used in Python. We have one in Java, and some of them support C++. None of them work in Clojure, but this does serve over 99%, I'd estimate, of the machine learning community. And if these already work and have such good support, why do we want to use Clojure? Turns out there's a decent intersection between functional programming and machine learning that people haven't really thought about too much. And the first aspect of this is the idea of function composition, which plays out very well in both theory and in practice. So in theory, if we look at neural nets again, and we look at the perceptron, which I mentioned before, as a function transformation between the 3 dimensions of the input to your single output y, and we call this F1. Then when we string these together into a neural net, what we actually have is a series of these transformations, where we pass in our input to our first set of nodes, which perform one function on it. Then we take the output of that and pass it forward as the input to the second hidden layer, and that performs a second transformation on it. So when we string these together, it's a composition of functions from input to output. It's a pipeline. And if you're missing the Clojure syntax a little bit, you can think of this very informally as a threading procedure. You can think of the prediction you make at the end as the output of this function composition where you've passed in the input to however many other layers and however many other function transformations you want. And you can view machine learning, especially deep learning as a whole in this case, as a process of optimizing the set of composed functions. So we have a bunch of hidden variables, hidden parameters that we're searching for, and we're looking for the optimal set of weights and parameters that would give us the transformation and give us the output value that we are looking for in the data. So in theory, neural nets match up very well with function composition, which is a core principle of functional programming. In practice, the entire machine learning pipeline, now regardless of whether or not you're using neural nets at all, is also performed in many cases as a set of composed functions. Because when it comes to machine learning in practice, neural nets and whatever algorithm you're using is only a very small part of it. You end up having to load the model configuration and load the data and do a whole bunch of transformations on the data. You have to clean the data if there are any inconsistencies or missing values. You have to extract features if your raw values aren't good enough. You have to shuffle the data around. You possibly have to augment the data. You have to do a whole series of transformations to get the data into a form that's appropriate for your machine learning model to learn from. And when you have this pipeline of transformations, what you have is a pipeline of functions that you're composing together to get your final output of the data. And this data is also passed into the algorithm, which is then processed in a feedback loop, which again is a pipeline that goes back and forth. So you can view this entire process again as a series of composed functions, where you're fetching the data from wherever you're storing the data first, and then you're doing whatever transformations necessary, in this case, cleaning it, encoding it into some other form, augmenting it, and then running the model and evaluating the results. All of this is one pipeline and one set of composed functions. Even outside of Clojure, it is most clean and elegant and effective to write this pipeline in a functional manner. So if we have both our neural net being shaped by function composition and also our machine learning pipeline shaped by function composition, then it makes sense to do machine learning in practice functionally. Now we want to talk about why Clojure specifically is so good for machine learning. So far I've been talking about why functional programming in general is useful for machine learning and why there's an intersection there. Clojure comes in when it comes to data processing. And I think Rich Hickey talked about this in the morning very effectively. He talked about how in systems engineering or any type of software engineering, you have a core bit of data or logic and a whole bunch of information processing surrounding it. And it's the same thing with machine learning, where in fact the most time-consuming part of the process isn't the building the model, building the algorithm itself, but actually the ETL or extraction, transformation, and loading of the data. So the data processing, it takes the most time and is the most grunt work involved with machine learning in terms of the process. So Clojure shines when it comes to data processing. One example of this is the fact that it provides things like lazy sequences. Machine learning models tend to, because they perform iteratively, they expect the data to come in batch form. You have batches of data that update the machine learning model one step at a time, and then you need to repeat the entire data set many, many times over to get a model that can stable out and reach an equilibrium in terms of how well it performs. So Clojure, by providing things like lazy sequences, you can very effectively augment data sets to become effectively infinite without having to load all of it into the memory and realize it all at once. So this is an example of some code that's ripped straight out of the Cortex library, actually, and I just want to display it because it's so simple and straightforward. You're taking in a finite data set, which is stored as a sequence of maps, so that's the map-seq, and then you're performing a series of function transformations over it. You're shuffling the data, you're repeating it an infinite amount of times, you're concatenating everything together, and you partition it into whatever size the model expects it as. And through this, you get a lazy sequence that's effectively infinite of the data set that you're expecting, so the model can process it and learn from it as many times as it needs. So that's one thing. Clojure has lazy sequences. Clojure also has really powerful built-in data structures. And I'm not going to talk too much about this. I'll talk a little more about this when we get to the specifics of Cortex and how it's been implemented. But essentially, we can do everything with the built-in data structures that end up giving us neural nets that are highly transparent and highly customizable when we want to work with them. So because Clojure is so good at the information processing part, and because Clojure was specifically designed to handle that problem of having so much information processing to do in any type of software engineering, when it comes to machine learning and the fact that the most time-consuming part of machine learning is in data processing, Clojure is a very good tool and a very good way of carrying all of this out. So I don't personally believe any tech talk is complete without a meme. I don't know about all of you because according to Rich Hickey, I'm in a room with a bunch of cranky old programmers, so I don't know if you'll appreciate this humor. But this is how it actually happens in practice. This is deep learning in practice, where a lot of people glorify it and think it's a lot more than it actually is. But in practice, especially if you're using Python, you are from Theano importing everything. So all of your functionality, everything I talked about for how you build neural nets, that's already built into some library for you, and you're just calling it and using it. Fortunately for us, that's a fairly good model because as end users, we don't actually have to deal with the nitty-gritty parts of anything. And that's why for us, if we want to work in Clojure, we don't import anything from Theano. We import it straight from Cortex. So Cortex is an open source machine learning library. It's been around for maybe 1 or 2 years, possibly more. It's been developed by my old company, ThinkTopic. And I had the opportunity to work a little bit on Cortex over the summer and see why it works. And over the first couple weeks I was working with it, I'll be honest, I was still very skeptical of why it existed in the first place. Like I said, I don't like reinventing the wheel. I thought this was reinventing the wheel. I wasn't in love with Clojure yet, like all of you are, so I was learning a new language and trying to be convinced that it was necessary for machine learning. But because of all of the things I talked about earlier, where I learned about how good Clojure is with data processing and how good the intersection between functional programming and machine learning is in general, I got a lot more interested in the development of Cortex. And there are a couple interesting parts that make us stand apart from a lot of the other libraries. So at its core, it's an open source machine learning toolkit. You can use it in the same way the meme used Theano. You can just import it and use a lot of its functionalities to build machine learning algorithms in very little code. It's built on top of a backend that consists of a compute library. So the compute library is a generalized framework that's designed to build and run algorithms efficiently on both the CPU and the GPU. It happens that machine learning algorithms train a lot faster on the GPU, so we actually have a GPU compute library that contains the CUDA implementations of all of these compute algorithms and implements all of that so you don't have to worry about it. So I'm not going to go too deep into the details of the compute library just because you will almost never interact with it. The really nice thing about the compute is it abstracts away almost all of the nitty-gritty, low-level computation-related details of the operations you're performing away from you. And that leaves us with the functionality of Cortex, which is built on top of the compute library. And the core design principle behind Cortex was to implement as much of the high-level details about neural nets as possible in pure Clojure. And the reason why that's so good is because you end up getting neural nets, the entirety of the neural net and the entirety of the traversal through the neural net, represented in pure closure data structures, such as maps. And this gives us a lot of transparency, a lot of control, and a lot of customization power into working with the neural nets. Because in other libraries, if they're implementing this in lower level C++ or other things that are shielded away from you as an end user, you can't go in and control the exact details of the neural nets. You can't go in and see quite exactly what the values of everything you're looking at in any given step you're looking at that easily. You kind of just have to trust that the algorithm works. In Cortex, you can trust that the algorithm works, but you also can very easily access all of this information and see exactly what you're building. And I'll show you what I mean in just a little bit. The way Cortex is designed in terms of the neural net is very similar to a lot of these other libraries. So for example, TensorFlow, which is arguably the largest machine learning library out there right now, implements its neural nets in the form of a directed acyclic graph. So you have your input coming in, you're performing a transformation, you're performing a matrix multiplication with it, with the weight matrix, and then you're passing that forward, you're doing an add operation, you're doing a nonlinear function transformation, so forth, until you get your final output. Cortex is designed the exact same way. We call all of the layer transformations nodes. We call the direction of the data flow edges. We call the parameters that we're holding and the flow of the data and all the memory that we're allocating for that data, the buffers. And then we call all of our inputs and outputs the streams. So Clojure represents all of these in the form of a map. And if you build a neural network in Clojure and you print it, you're going to get something that looks almost exactly like this. You have a compute graph, so that's your computation graph. And within this map, you have 4 keys. You have your nodes, your edges, your buffers, and your streams. And one nice thing about Cortex is for every single element within any of these 4 categories, it goes in and automatically associates a unique ID to it. So for your input under nodes, you automatically get the ID of input 1, and you can see a map of all of its properties. So the dimension of the input that's flowing in. You automatically get the first linear layer and all of its properties. And when you get to things like buffers, it automatically allocates space for linear layers because it knows that when you have a fully connected layer of neurons, there are weight matrices associated with it. There are bias vectors associated with it. So you get not only the names of these, but also the random initialization, or as you go on in time, the not so random initialization of these parameters, and you can go in and see the exact values that you're working with. So in Cortex, at any given step, if you need to debug your neural net or need to learn more about it, you can go in and look at all of this. You can figure out what's going wrong or going right. And with these unique IDs, you can very easily update information in any part of this. You can very easily associate new properties, get rid of old properties, come up with your own specific loss functions, for example, come up with various little tweaks that you want to introduce to the neural net. And Cortex will respond accordingly because this is exactly what it works off of. And you don't get that type of low-level control in any other library. So if this is how Cortex neural nets look, I want to now walk through the basic steps of how you would build up a neural net in Cortex. So there are a couple basic steps to building a model. The first one is loading and processing the data. So that's what we were talking about earlier with ETL. This tends to be the most time-consuming step until you get into actually tuning the model and trying to improve the model, and then that's your most time-consuming step by far. But the first step is just loading and preparing your data. Your second step in Cortex is defining a very minimal description of what your neural net will look like, and that's just a description of what layers you want in what order. And your third step is to build a full network from that minimal description. That's just a single function call, and training the model on the data that you've loaded. So with these 3 steps, you can actually train and evaluate your own neural net on any data set of your choosing. As an example, I chose a credit card fraud data set, which was interesting to me for a couple reasons. One of them is that this is actually how your credit card companies work and how Amazon works and Walmart works. they use machine learning algorithms to evaluate the purchase that you're making against all of your other past purchases or past usages to try to determine if this was fraud or not. In almost all the cases, it's not fraud, but in the 0.1% of times that it is fraud, it tends to be that it's a pretty big purchase, and it tends to be something that you want to catch in a model. So if we go back to the diagram that we had at the beginning, we can think of the past user's card usage as the data that you're feeding in. So how often you use the card, for example. How much did you usually buy? How much money do you spend? How often do you shop? All of these details about the user. And then we have a label. So now we have a data set of past purchases and confirmed frauds or not fraudulent instances. So you have your data and your label there. You pass it into some algorithm in Cortex, and you end up generating a neural net that has learned the proper weights to associate with the data in order to give you your proper prediction. Then when you want to actually use it in practice, all you have to do is feed in the card usage to this model, and it can make a prediction on whether or not the purchase that was just made was fraudulent or not. So the first step of this is data loading and preprocessing. One thing I want to emphasize is this is the bare minimum of what you have to do. Like I talked about, it tends to be that in real-world machine learning, it's never this simple because there's a lot of middle steps to actually transforming and cleaning the data. This kind of assumes that the data has been handed to you in the perfect form for a machine learning model, which never happens in real life. But the nice part is that, like I talked about earlier, whatever transformations you have to do to the model don't get too much more complicated. You just write up the functions and you string them together as some form of composition of the functions. You pass the data through them and you get the data outputted in the form that you want for the neural net. So the key parts to this minimal example, you want to identify obviously where your resource is. So now we're assuming that the credit card data is being held in some CSV file somewhere with all of the information that you need. You would load this file into memory, of course, and then you would separate out the data from the labels. So this is one area where you're assuming that the last column in your data set, so the drop last, is the label. So when you're grabbing your data, you're grabbing everything but the label, and you're converting everything into a number so the neural net can process it. For the label, you're doing something very similar. You're grabbing only the last column, you're mapping everything into a number, and then you're calling a Cortex function that transforms this class into a one-hot vector. A one-hot vector is something that is used to represent the output of some classification task, essentially. So when you have 3 different possible classes, you take whatever class it is and transform it into a 3-dimensional vector where each column corresponds to the existence of that class. So if it's the first class, you get 1, 0, 0. If it's the last class, you get 0, 0, 1. And the only reason we do this is because the model outputs predictions in this way. It outputs the probabilities for every single class. So when we generate the labels, we also want it in a matching form. And finally, we associate the data and the labels to the corresponding ones that we've actually grabbed. So Cortex actually expects its data sets in a form of sequence of maps, where each map corresponds to one training instance in your data. So for example, you can have data and a set of numbers that each number corresponds to some variable in your data set, and you can have a label of 2 classes. So in the first, third, and fourth example, it's one class. In the second example, it's the other class. So through these steps here, you can generate a data set that looks something like this. And in this case, you're done with loading your data. This is all Cortex expects from you with the data. When you want to build up your model description, it's also very straightforward. The first step is simply writing a definition of the network as a series of layers. And this is the layers of the neural net in the order that you want them in. So in this case, we can see we have an input. We have a linear layer, which is just a fully connected layer that uses the rectified linear unit activation function. We have a dropout. We have some more linear layers. In the end, it maps to something that looks like this, where you have your data coming in. You have another layer corresponding to the second blue column you see here, and so forth, and a dropout layer in the middle, which is just another transformation you can have that essentially ignores certain parameters during training to make the model more robust and more generalizable in the future. So this is one particular architecture of a neural network you can train. You can tweak the numbers here or tweak the layers that you want to see here to correspond to whatever neural net that you're trying to build in practice. So creating the model itself is just a series of definitions for the layers that you want to see. The final step is training the model that you've just described on the data that you've just loaded. So with every neural net, there are a set of hyperparameters associated with it regarding, say, the size of the batches that you want to train on, how many times you want to train it, so forth and so forth. So you can specify all of these parameters, and then in your actual train function, you first build the full network from the description that you just had. So this function transforms the very minimal description we saw here into the full-blown computational graph that we had earlier. And that was the graph that contained the nodes, the edges, the buffers, and the streams. So once you call this function here and you print the network, you can actually see that output, and you're going to see the weight matrices initialized with random numbers in it. You can then split up your train data set. You can split up your train data set into a train portion and a testing function, testing portion. And with your train data set, you can make it infinite. So this is a function that's almost identical to the one I showed earlier. That's just infinite data set. It just so happens that because it's a classification task, you can also balance it by the class. So you can have an equal number of positive examples as negative examples. And then you can call one single function to do all of the rest of the work for you. So in the experiment library, we have a train-n function, train network, and you just pass in all of these variables that you've created earlier. So the network, the train data set, and the testing data set, and you pass in all of your hyperparameters. And this function will not only train your neural net, but it will actually evaluate it on the testing set for you and print out your output for how well the model is doing at each step of the training. So in theory, at this point, you can actually get up to a fully working model, and you can see exactly how well it's performing on the data set that you're testing on. Through these steps here, the loading of the data and the description of the network and the training, you've gotten to a point where you have a fully functioning neural net that you can theoretically deploy into practice in production. Obviously, there are a few more steps that are involved if you want to make this neural net work well. On the particular credit card data set I was using, just these steps left me with a very, very, very bad model. So there are some extra steps that are involved, and this gets more into machine learning theory and practice than what we want to go into today. But you can do feature selection, so you can pick out features that are more useful than others. You can tune the hyperparameters of the model, or just tune the model to use a different architecture altogether. And you can do data augmentation and generate artificial new data based on the data you already have and train on the data augmented data set. But with a combination of all of these steps, you can get up to a very solid working neural net model. In this case, with the credit card data set, we achieved fairly good results with an F1 score of 0.84. That's pretty decent for the credit card data set because it's extremely unbalanced. It has like 0.1% positive examples. And this is the process that you can use to train on any arbitrary data set, essentially. So using these combinations of steps and using any of these additional model tuning steps after building the initial model, you can get up to a working model, and that's how Cortex works in general. So if we want to look at the big takeaways, we can see again that the neural nets and machine learning pipelines are just a composition of functions. We can view neural nets as an optimization of the composed functions, and we can view machine learning as a pipeline of these composed functions. So we can see that machine learning and functional programming intersect together very well. And we can also see that Clojure is very good at handling information processing and data processing. And for these reasons, Clojure is very good and very applicable for machine learning and the machine learning space. Clojure on Cortex provides you with a very high-level interface for designing and training your neural nets, which not only gives you simple initialization processes, but also gives you a very high degree of control over how to design your neural net and control the exact outputs and inputs and weight matrices inside, which gives you the full spectrum of using it for research purposes to using it for production purposes, for using it to learn machine learning in general. So if you're interested in machine learning at all, or if you're interested in Clojure at all, give Cortex a try. And if you have any more specific questions on Cortex, you can feel free to come talk to me after the talk, or we have some folks at Think Topic here who I'm sure would be very happy to talk to you as well. So thank you.